Hello and welcome. Today we're diving into space weather, the conditions in space driven by our very own sun. It might sound distant, but its effects can be felt right here on Earth, impacting the technology we rely on every day. Understanding and predicting space weather is a fascinating mix of science and engineering. So where does it start? At the sun? Three main things cause space weather: solar flares, coronal mass ejections, or CMEs, and high-speed solar wind. Solar flares are intense bursts of radiation, mostly X-rays, that reach Earth in just 8 minutes, traveling at the speed of light. They mainly disturb the ionosphere, the upper charged layer of our atmosphere. Then there are solar energetic particles, or SEPs. These high-energy particles, often linked to flares and CMEs, arrive within minutes to hours and pose a radiation risk. Finally, the big ones. CMEs. These are enormous clouds of plasma and magnetic fields hurled from the sun. They travel slower, taking 1 to 3 days to reach us. When a CME hits Earth's magnetic shield, the magnetosphere, it can trigger geomagnetic storms. Our magnetosphere protects us most of the time, but strong events can really shake things up. How do we see these events coming? Prediction involves constant observation and clever modeling. We have eyes in the sky like NASA's SDO and SOHO, watching the sun constantly, spotting flares and CMEs. Satellites like NOAA's DSCOVR sit between the sun and Earth, sampling the solar wind to give us a heads up, usually 15 to 60 minutes before a disturbance arrives. We also have ground telescopes and sensors monitoring Earth's magnetic field and ionosphere. All this data feeds into complex computer models. Some use physics to simulate the journey from sun to Earth, while others leverage artificial intelligence and machine learning to find patterns and improve forecasts for things like flare probability or CME arrival time. Centers like NOAA's Space Weather Prediction Center analyze all this to issue watches and warnings. Why does this matter? Because severe space weather can cause serious problems. Satellites can be damaged by radiation, affected by increased atmospheric drag which alters their orbits, or suffer electrical charging issues. Power grids are vulnerable too. Geomagnetic storms can induce currents in long transmission lines, potentially damaging transformers and causing widespread blackouts, like the one in Quebec in 1989. Communication systems can be disrupted. Solar flares cause radio blackouts, affecting HF radio used by planes and emergency responders. GPS accuracy can degrade. Aviation faces risks from increased radiation, especially on polar routes, and potential communication or navigation problems. And of course, astronauts in space are directly exposed to harmful radiation from SEPs. Given these risks, how do we protect ourselves? That's where mitigation engineering comes in. For satellites, we use radiation-hardened components, shield-sensitive parts, put them in safe modes during storms, or even adjust their orbits. For power grids, operators monitor induced currents, adjust operations based on forecasts, and upgrade hardware to be more resistant. Communication and navigation systems rely on forecasts to anticipate problems and have backup plans. Airlines use space weather predictions to reroute flights if needed. Ultimately, better forecasting is key. Improving our observation networks and forecast models, including using more AI, gives everyone more time to react and implement protective measures. Looking ahead, our reliance on technology makes space weather resilience even more crucial. Future efforts involve developing more advanced, integrated models, launching new observation missions like ESA's Vigil, fostering international collaboration because space weather is global, and continuing to engineer more robust systems across all sectors. By combining cutting-edge science with smart engineering, we can better safeguard our connected world against the unpredictable moods of the sun. Thanks for listening.